Hello, everyone. My name is Ganesh Thakur. I'm a professor of petroleum engineering at the University of Houston. My topic today is on carbon storage focused reservoir management of a mature Indian oil field in response to climate change. First, I would like to share vision for minimizing global fossil fuel emissions. Second, I'll discuss the carbon disposal options. Third, I'll talk about the examples of anthropogenic CO2 EOR projects around the world. Next, we'll discuss the intelligent reservoir management requirements for preparing a stacked pay reservoir for miscible injection and gas storage for CCUS and CCS projects. Why injection in an existing oil and gas reservoir is desirable in the early stages of carbon capture, utilization, and storage. Then we'll discuss several key optimization variables, and we'll investigate those. We'll discuss depletion plan under primary recovery, then for water flood design and location of the injection wells, and then CO2 injection design. The depth and injection parameters for injection wells will be analyzed. Then we'll discuss a pilot program and full field injection program, how we developed it utilizing a calibrated dynamic simulation model. Then model calibration is performed using field and lab data that makes the model more robust, thus developing more confidence with the prediction. And finally, we will share the optimum parameters for the injection program, how they are designed using a genetic algorithm, and storage volume, how it is maximized while minimizing cost and risk. As we all know, if we look at the global fossil fuel emissions, there is a tremendous motivation for all of us to reduce the emissions. If we look at on the vertical axis, the gigatons of CO2 emitted by various countries, we see China here right at the top, followed by US, followed by India. I'll be discussing examples for the cases from India. So that will be my focus point for focusing on the emissions in India and how the projects have been designed for Indian oil fields. Carbon disposal options, we're looking at direct geological storage, injection of captured CO2 into deep saline aquifers, injection into depleted oil or gas reservoirs, and CO2 utilization for enhanced oil recovery and other possible industrial usage, and how CO2 can be stored as natural sinks in soils and vegetation. My focus point is going to be on the top two bulleted items. Right here, direct geological storage and CO2 utilization. If we look at a variety of projects for anthropogenic CO2 EOR projects around the world, we see projects in Saudi Arabia, we see projects in Brazil, Santos Basin. We'll look at Sleipner project for Statoil in Norway, Petronova project near Houston, and Gorgon project for Chevron in Australia. Various projects in Japan and China are in the early phases of development. And we at the University of Houston are involved in carbon capture projects in India that I will be discussing briefly during this talk. Outline of this presentation involves, first I will introduce the project, then we'll discuss about the reservoir background, then we'll talk about the analysis and results, then we will provide a summary and conclusion of the presentations. As we all know, CO2 injection is a proven enhanced oil recovery method. It has a dual purpose, enhancing oil recovery and carbon storage. As we see here, CO2 is getting injected in the reservoir. It displaces the oil miscibly, and then CO2 and oil is produced at the production well. Reservoir management is critical to ensuring the injection success. Reservoir management leverages an integrated understanding of the field. Reservoir management connects the dots between the primary recovery of oil, secondary recovery, and enhanced oil recovery, and then enhanced oil recovery coupled with maximizing the storage of CO2 in the reservoir. That is called the EOR plus. For University of Houston projects, with CCUS projects, we perform these projects in 3 phases. Phase 1 is the screening project. Phase 2 is where we focus on the design of the pilot, lab study, simulation in detail, 3D geological modeling, history matching of the simulation model, CO2 EOR simulation, then designing the pilot, including the CO2 source study, facilities and completions, risk assessment, and economic analysis. And phase 3 focuses on CO2 EOR pilot and field-wide implementation. We pay very close attention to a rigorous surveillance and monitoring program involving pressure, CO2, and so on. And then finally, optimization of the EOR and maximizing the CO2 storage. This is our lab facilities where we carry out the CCS, CCUS projects, lab experimental work. The key objectives are involving the improvement of reservoir characterization and modeling, unlocking the full potential of conventional and unconventional resources through CO2 and gas enhanced oil recovery, and maximizing CO2 storage for CCS or CCUS projects, and also making sure that the CAPROC studies are performed for its robustness for CO2 storage. We perform the detailed studies of the CO2 and gas enhanced oil recovery for both conventional and unconventional reservoir, and also CO2 injection in aquifers. We perform the lab and simulation studies, reservoir conformance, characterization, conformance control, and sweep efficiency, optimizing the well patterns and placement of fractures, integrated reservoir well facilities studies, and the effective reservoir management in CO2 enhanced oil recovery and storage, including saline aquifers and depleted fields. And then technology transfers, and we are involved also at this point in time with Permian Basin projects. If we look at the brief history of CO2 injection in the Permian Basin and in the US, CO2 fields were discovered, namely the Bravo Dome, McElmo Dome, Jackson Dome, and Sheep Mountain. These are naturally occurring CO2 fields. They were developed and tested in 50s and 60s. The first notable CO2 EOR flood was performed in the Permian Basin in the Sac Rock unit. First notable CO2 EOR flood was performed in the Gulf Coast in the Little Creek field. And in the 80s, CO2 EOR flood was performed in Rockies, in Rangeley. And first anthropogenic CO2 EOR flood was performed in the Weyburn field in Canada. And first commercial scale anthropogenic CO2 project in Texas was conducted by the Petronova project near Houston. So there is a huge amount of CO2 injection experience that can be leveraged for carbon storage projects in the US and around the world. Case study, we look at first commercial CO2 EOR project in the Sac Rock unit in the Permian Basin. First commercial scale CO2 project that was conducted in 1972 in the Permian Basin. That unit covered over 50,000 acres and was formed to optimize secondary and tertiary recovery of oil in the Canyon Reef. It involved 3,900 miles of CO2 pipelines in the field with a variety of projects that were involved. Oil production showed a quick response to CO2 injection soon after the peak water flood production response occurred. And CO2 enhanced oil recovery added more than 10% of the incremental oil recovery. As you see here in the footnote, actually this project started as an anthropogenic project. CO2 in this field was supplied from the gas plants where the CO2 was captured and then transmitted to the field. So in a way, this is the first anthropogenic CO2 project in the world in 1972 that occurred in the Permian Basin. So let's see the performance of a particular area of the Sac Rock unit. So this is the 4-pattern area of the field as shown right here. And there was another area that is 17-pattern area. So today we're going to focus on this 4-pattern area and we're going to look at the performance of CO2 injection in this particular reservoir. So on the vertical axis, you look at the barrels of oil per day. On the horizontal axis, you look at the time. And here, first you see the decline rate established during primary and secondary recovery. And as soon as the CO2 injection starts, please look at the performance of the CO2 flood. It is causing a tremendous increase very soon as a result of the CO2 injection, and the benefits are seen here in terms of the oil production. Pilot conducted in south part of the unit in the 4-pattern area. It consisted of 160-acre inverted 9-spot pattern. And as you can see from here, within a year or so, over 2,000 barrels of oil per day of definitive oil response occurred. And the EOR accounted for over 10% of the additional recovery after 30% hydrocarbon per volume of CO2 injection. So this is a great example of how CO2 can be used for enhancing the oil recovery, at the same time, how CO2 can be stored in the reservoir. Now, we are moving to a reservoir in India. The reservoir background, a mature Indian oil field. It is a sandstone reservoir. It is interlayered with calcite, cemented, and coal-bearing zones. And it is shallow marine to lagoonal conditions with fluvial influence. So we first developed a 3D geological model for stacked pay reservoir, as shown right here, consisting of 4 phases, which are shown right here, of good quality phases, the medium quality phases, the poor quality phases, and then the non-reservoir rocks. And we perform a rigorous reservoir characterization and simulation study of this particular reservoir. As you can see here in this reservoir, compartmentalization also plays a very important role. The pressure depletion and the water cut evolution trends reveal 2 major compartments in this field. And this observation was confirmed by subsequent geochemical analysis in the field also. Clustering performed on various production trends using the dynamic time warping algorithm, measuring similarity between 2 sequences. And with sand continuity analysis from petrophysics, with the pressure depletion trends seen in the field, locations for pressure support were determined, and they are labeled above here A, B, C, and D. So this particular reservoir has an aquifer support from the bottom, very strong aquifer support from the edge, and the reservoir pressure is also reasonably well maintained in this field. So understanding the aquifer direction and the strength in this stacked reservoir, which shows here going from zone 0 to zone 8. The water cut trend analysis with various depletion profile indicated the direction and strength of a strong edge and weaker bottom water aquifer system. The aquifer water movement was consistent with the petrophysical analysis acting in a northeast-southwest direction. There is a strong pressure support and water production trends that indicate a sizable and well-connected aquifer, another potential carbon storage site. Production analysis with petrophysical analysis aid the selection of the injection locations with maximum carbon storage and or EOR potential in this field. Static and dynamic reservoir modeling was performed rigorously. A full cycle of analytical study followed by static and dynamic modeling was performed. 3D geomodels were developed based on provided seismic surfaces, well tops, core data, and petrophysical results. Production pressure data analyses were incorporated with facies trend maps from log data to yield the facies model. And calibration of the numerical simulation model was performed by integrating production, pressure, and petrophysical analysis. And the calibrated numerical model was used to optimize the injection parameters. Results of the injection optimization. The purpose of the optimization was to use the calibrated numerical model, which were history matched, to find the optimum injection locations and production rates. Optimization performed with history match model. And optimum injection locations were selected to repressurize the reservoir and optimize the reservoir recovery. And here, minimum amount of water was injected, and the repressurization of the reservoir happened as a result of CO2 injection. We see the optimization objective function, where J is the objective function to be minimized. Delta P is the difference between the initial pressure and localized grid block pressure, and SG is the free gas saturation, and alphas are the weighting factors, and they were set to 0.5 in this case. Table on the left shows CO2 storage potential of the field over 11-year injection period. Pilot injection consists of 2 patterns, and the full field injection scheme includes an additional 5 patterns, making 7 patterns in total. And CO2 injection is performed without prior water flooding. CO2 initially is immiscible, but turned miscible after 1.5 years, and injecting CO2 without a prior water flood yielded more pore volumes of storage of CO2. So as you can see, for the pilot, the incremental recovery of about 11%, for the full field, about 10%. And CO2 storage for the cases are shown right here. Aquifer carbon storage potential. We also investigated that how much CO2 we can store in this aquifer, especially by producing the aquifer. This table highlights the additional storage created by producing aquifer water using the current well bores. An additional storage potential within the reservoir aquifer system, where high water cut wells are produced and injection maintains the voidage replacement. So EOR and CO2 EOR and storage for the Oil India project started in 2016-17. First, we performed a screening study of the 50 reservoirs containing some 2.5 billion barrels of oil in place. Then we did a CO2 EOR scoping study, the pilot design. We performed all the lab work, slim tube, minimum miscibility pressure, swelling test, core floods, simulation study, history matching, pilot design, and now the implementation and economic analysis. and CO2 capture and transportation by truck. And as the project matures, then CO2 transportation can occur by rail when it involves larger or several reservoirs. Transportation by truck is suitable for a smaller quantity of CO2. Trucks are planned to be used, moving the CO2 from where it is captured to nearby EOR and storage locations. And this is the Brahmaputra Cracker and Polymer Limited, BCPL, CO2 source, and then the CO2 will be transferred in trucks and injected near here in the reservoirs and also in the aquifer. So looking at the summary and conclusions. CO2 injection increases the recovery factor of oil from the reservoirs by about 10 to 11%, while storing CO2 for the pilot area, a smaller amount, and for the field-wide 5 million tons of CO2. It yields a gross CO2 utilization ratio of 8 to 13 MCF per barrel of oil. Continuous CO2 injection scheme maximizes both storage and optimized oil recovery. And CO2 injection occurs continuously for 11 years. This volume honors wellbore, rate constraints, and CO2 supply limitations. The reservoir, as we discussed, is underlain by a large aquifer, several times larger than the reservoir pore volume. There is a large storage potential in the aquifer. And by depleting the aquifer, an additional storage potential exists in this field. While the reservoir storage potential is approximately 5 million tons, there are more than 50 other candidate reservoirs within the portfolio of the client company. These add up to 2.5 billion barrels of oil in place, a large storage capacity. The size of the prize is extremely large, considering many of these reservoirs are connected to large aquifers. The water produced by various production wells, which many have water cuts greater than 90%. This water can be treated and used for other purposes, such as agriculture. This has two benefits. First, the produced water leaves additional pore volumes for carbon storage. Secondly, the produced water is an alternative water source, which is especially important in drought-prone areas in India. I would like to acknowledge my colleagues from the University of Houston and the client group of the companies in India. And I would like to thank you for providing us an opportunity to share our technical work. And I will be glad to answer any questions that you may have on this subject. Thank you very much.